right, let's set up a couple examples in a row. Okay, I'd like to do 3 examples to help get us more used to what's going on with setting up these integrals. So I'd like to set up the integral for f of x comma y comma z equals 1 over the solid sphere of radius 9. Now here's the thing. If we integrate 1 over the solid sphere, what is it that we're computing here? Think about what you're always getting when you integrate the function 1. In triple integrals, you're getting a volume, right? We're really just getting the volume of that sphere. So the bounds of integration are just like what we saw in the example that we did. So we're integrating the function 1. dv becomes rho squared sine phi d rho d theta d phi. And the rho bounds were from 0 to 9, just like the previous example. The theta bounds are 0 to 2 pi. And then the phi bounds are from 0 to pi. Now here's the really wonderful thing about this. We're just done because we said set up. But this integral actually can be done without all that much work, which is actually fantastic because I think it's kind of hard to memorize the volume formula for a sphere. Of course, you could look it up. But the point is, you can just get it here. The only question is, where the heck did this rho squared sine phi really come from? Why is it really that? But if you could be convinced of this, then you actually have a rather nice method of computing a volume of a sphere instead of just believing somebody else when they say you have a volume of a sphere. So I'd like to also work off of this and talk about the volume of the bottom half of the same solid sphere. So the solid sphere that we were describing up there. So how would the integral look different? This is what I would like to discuss. Right? So I'll write the same 3 integral signs. Still write 1 times rho squared sine phi d rho d theta d phi as before. But to try to make sense of what's going on with the bounds of integration, let's talk through this carefully for the bottom half of the solid sphere. So rho, still from 0 to 9. Okay, the radius hasn't changed. Theta, okay, that's as you sweep around in the xy plane, that's still 0 to 2 pi. Okay, but what about phi? Now, we want the bottom half, meaning the part of the solid sphere that's under the xy plane. So all of those points that are under the xy plane, pick any point under the xy plane, draw the straight line segment connecting that to the origin, and compare that line segment's angle made with the positive z-axis. That angle is always obtuse, always bigger than 90 degrees. So this should go from pi over 2 radians, 90 degrees, all the way up to largest possible value, pi. I'd like to do one more follow-up to this. Again, we're just going to do another setup just to try to get comfortable with what's going on. And what I'd like to do is modify the last example just a little bit and talk about the volume of, well, the following shape. Actually, I can do that. And then here I've got so what's the shape I'm trying to draw here? This is a seeded melon. Meaning if the last example here was the bottom half of a solid sphere. Oh, that was terrible. Let's try just drawing the equator first, and then the bottom half of the sphere. And this is completely filled in, right? Just then if you scoop out the seeds in the middle of this cantaloupe, then I guess it looks like this, right? And here I'd like to intentionally have the inner radius being 4 and the outer radius being 9. So yeah, the distance from, say, right there, so it's just a point hovering right there to the outside edge is 9. So yeah, this distance is 4, and then that distance is 9. So it should be just a slight modification of the previous picture. The volume should be a little smaller because we're cutting out a little bit of that seed area. And so it should be roughly the same integral as we just saw. So 1 rho squared sine phi d rho d theta d phi. But what's different now? So we still have the bottom half of the melon, right? We just removed more, so the bottom half still pi over 2 to pi. Theta, still going all the way around. We've gone all the way around this thing. Okay, so this should, just like we went all the way around here, so we have still 0 to 2 pi. But the difference is the values of rho, right? We've intentionally now cut out, by removing this middle core area, we've cut out all of the points whose distance from the origin is 4 or smaller. So, well, let's say smaller than 4. We cut out those. So this should just be an integral where rho goes from 4 to 9. Okay, let me just comment that this setup was we're done basically, and I will say that this integral is actually nice to do. But if you were to try to do this in cylindrical coordinates, this would be very challenging. So this seeded melon, it'd be very challenging, very hard, I think, to describe even just the bounds of integration in cylindrical coordinates. But this shape, it's actually very, very natural, just constants on all 3 integrals, in fact, to describe this in spherical coordinates.